Welcome everybody to the American Space Museum. I'm Marquette. We're so glad you're with us to stay curious. Today with Jeff Andress, a thermal protection system engineer, and I'd say pretty much an expert. Hello there, Jeff.
Hi, Mark. Thanks for having me.
Well, we're glad to have you here, and thanks for Marty Winkle, my co-producer, for efforting you. Marty, how you doing today as we crack open that UCAC microphone? Hopefully people have a lot of questions today, so keep your eye on that.
Okay, I'm doing fine. I'm finally dried off. Hopefully Jeff dried off also.
It's a little wet.
It's raining outside, Mark.
Yes, it's raining outside, and we've got a lot of lightning going on. So if we do go off air, we'll be back someday. But we're well into our 870 episodes, Jeff, of doing conversations with space workers who our museum celebrates space workers like none other. We actually think you're national treasures. And we firmly believe that because of your involvement with the 3-decade-old shuttle program. And now I understand that you're involved with the Starship of SpaceX. So tell us a little bit about yourself, Jeff Andress. Where'd you grow up and how'd you get involved in all this?
Okay, so I started out in Southern California. That's where I was born, in Long Beach, and my dad went to work for North American Aviation in 1966. And via his employment, we made our way to Florida in 1968. And he was involved in the Apollo program, and he was an inspector there. He worked on the S2 for the Saturn rocket, and that's how I ended up here. And I remember very shortly after moving to Titusville, seeing my first spacecraft launch. And it was from Riverview Elementary School when it was out there still on US 1.
Which elementary?
It was Riverview.
Riverview.
It used to be on US 1 and part of where the Titusville High School campus is now. And we all ran outside and watched the rocket go up. And then the next launch that I saw was Apollo 8 in December of 1968. And that was quite a vivid memory because it was a very clear day. It was cold. And we had good winter air, and it was very clear, and so you got to see the rocket go up very slowly, and then it was a great flight, and it was manned and successful. So I think that was very exciting for me. It certainly was a big deal for my family, and then my dad worked the Apollo program all the way through until the Apollo-Soyuz missions were done, and so yeah, that was kind of my intro to space flight. I really, at that time, early in my life, didn't think too much about being part of the space program. I just thought it was a cool thing that America was doing. And so
looks like you may have toted a surfboard around a little bit. Is that true?
I wasn't a surfer. I did
okay.
skateboard quite a bit.
Oh, skateboarder.
Yeah.
Okay, land board. All right.
Yeah, that's right.
So yeah, I was going to ask you. So you're looking Apollo baby, basically. What was your father's first name?
His name was John.
John Andrus.
Yep.
And what contractor did he work for?
He worked for Rockwell up until about 75, and then
because we have a lot of people watch Stay Curious. John Andrus, your dad. We see a lot of father, son, daughters, and also follow each other in this incredible American space program.
yeah, that's right. That's right.
And so you saw your first launch so vividly on that cold December day in 1968, and then 1988, 20 years later, you're involved with the shuttle.
Yeah, that's right.
How'd that happen?
So I was 20 years old, and they were looking for temporary tile technicians to work on the shuttle. My dad was working on the shuttle program at that time. And he had put my name in the hat with somebody there, and I had put an application in, and I got a call for an interview, and I went to work bonding tiles on Columbia when it was here in 1979.
Wow.
And so yeah, just shy of 44 years ago next month.
Absolutely, yeah. So you got a special bond with Columbia Orbiter 099 tail number in the
102. 102 actually.
102. I'm sorry. Yeah, Challenger's 099.
That's right.
Yeah. 102 actually is the. Thanks for correcting me. See, I'm just trying to be smart, and I'm not. By the way, Jean Wright's watching. She says Jeff is so smart up there, and also Susie Cunningham says hi. She's been involved with our space museum, as well as Gene has. So two good friends there, spreading the word to watch Jeff Andress here, thermal protection systems in the shuttle era. We're going to get into some details about how the shuttles work, what they're made of, as well as now working with SpaceX on the mighty Starship out there. So you're working here in Florida. Well, the physical, I mean, the Starship, have you been out there? It just looks incredible. It's so sci-fi to see all those starships out there
Yeah, it's
standing around.
it's vast. It's big.
It's vast. I know you can't say too much about it without letting the cat out of the bag and getting in trouble, but can you tell us, are things going well? Are you on a trajectory that SpaceX wants to be on to get the Starship up
Absolutely.
and on the moon?
Absolutely. I think things have progressed extremely rapidly compared to historically. NASA programs have taken a long time to develop, and SpaceX is very progressive in the way that we adapt to engineering changes to be successful.
Mm-hmm.
And so it is definitely moving forward at a good pace, I would say. And we're trending toward success.
Well, good. We're looking for it being on the moon in 2025 or somewhere around in there.
That would be awesome.
And the next launch is rumored to be in the next months or so. Can you tell us anything about that?
I cannot. I do not know those schedules, and
Okay.
and I know that there's a lot of people working that. So.
Well, how do you feel working the 30 years on the shuttle? And really, we brag all the time, Jeff, about how the 30-year decade of the 30 years of the shuttle's changed. It's why we're living the way we are today in the 21st century, with everyone's got a computer in their pocket. Everybody's got instant communication. The satellites put up, the infrastructure, the space station itself. Yeah. You had a part of that. And so how you feel about that as you're working now to go to the moon?
I feel super fortunate. Like I've had an amazing career to be a participant. There were many participants. It was a huge program with a lot of really talented and educated people, people that really put their heart and soul and minds into those vehicles and flying them safely. And it just it was at the time. Everybody was so spread out, and I think that we all contributed kind of on a small part to a really big success. So at the time, it was a bit of a stretch for most of my career to take a lot of pride in that. But as we started to mature, both in age and the program, we started to realize what a resource it was and how much it had accomplished. And I think everybody that was participating in that became, very proud of their role in it. And certainly the same is true for me.
Well said, Jeff. I think that's exactly the way we feel about the American Space Museum and how we promote our museum and the artifacts is that, one of the giant shoulders that's being stood on right today is you people in the shuttle era. So many pieces, parts, so much intricacy to it. And we're going to talk about the tiles up above here, our beautiful green screen back here. You supplied that picture, Jeff. What are we looking at there?
You're looking at the wing of the Discovery, OV-103 on orbit. As it approached the space station. I'm sure that was the R-bar pitch maneuver that they took pictures from the station just to take a look and make sure everything was in good shape before they docked. And
you're going to point out something in there a little later
so
for everyone to stay
right.
curious with. It was a little piece of engineering that you're going to tell us about.
Yep.
So, well, let's Marty, let's look up here. I wanted to tease everyone that we've got a recorded interview with astronaut Mike Baker. Tomorrow we're going to air that. He had a great conversation with me about his 4 missions, twice a pilot, twice a commander, but he was also 5 years the key NASA person in Baikonur for the launch of our astronauts on the Soyuz spacecraft of the International Space Station. So Mike knows a lot about the Russian culture as well as the European culture, and he contrasts that a little bit with America. So you're not going to want to miss Mike Baker tomorrow on a recorded interview, a great guy. But today we got Jeff Andress, TPS Materials Thermal Protection System. That's a acronym I learned quite quickly hanging around the American Space Museum. And so you're going to tell us, here's your experience a little bit. You were 8 years involved with upgrading the shuttle. Tell us the highlights there. 26 years engineering. Now you've been involved with Orion, Dream Chaser. We're going to talk a little bit about the Dream Chaser. And then, of course, someone with your expertise becomes a manager on the floor like that. So physically, where was this building at?
So I started out in the orbiter processing facility where most of the tile maintenance was going on. There were 3 hangars that were processing facilities, and so the first 8 years of my working with shuttle was primarily in those rooms. A little bit at the pad, a little bit at the VAB, prepping vehicles for flight, but most of my time was spent in the orbiter processing facility, either removing and installing tiles and sometimes doing modifications, but mostly just standard integration and maintenance work.
Worker bees, one of the worker bees.
Absolutely.
Like the good worker bees become the good leaders and the good managers, of course, like you did. So we the history of the tile and the difficulties, and 30,000 of them on an orbiter has been well documented. What do you have to say about that part of the shuttle era? That you had challenges, but certainly you overcame them and understood, I think, anomalies when they came up.
Yeah, it was a very labor-intensive system. All of the bonding, all of the prep work to get the parts in the right condition to fly, to minimize steps and gaps so it performed as good as it could. Certainly was a challenge. And the materials, I think, early on, the original design of shuttle, you were talking about the early 70s when a lot of these products were developed, and so they were cutting edge in the late 60s and early 70s, and there was still some evolution that probably could have been carried forward faster. But when you certify a vehicle for 100 missions, there's a tremendous amount of testing that went into that 100 mission certification. And so to go back and make alterations or changes to the design became, a real a heavy burden for the program to go in and investigate what needed to be investigated to say, hey, this is a good interchangeable product for what we've already verified. And so making upgrades to the thermal protection was kind of slow, and like you said, it was a ton of tiles. And so how much of that do you really want to go after in between? If you have a 60-day turnaround time for a vehicle, how much can you really go in and change? And so a lot of the upgrades happened at major modification periods when they were modifying a lot of the other components on the shuttles as well. And that was kind of later on in the program, but certainly early on, we started out with just all silica components with a glass coating that was very fracture prone, very damage prone, and low impact resistance, and so it took until almost 2000 before we really started to improve the coatings concurrent with the insulating material underneath, and make some real forward progress on damage resistance and stronger components.
Very interesting. It goes through my mind. You were talking about the one certifying it for 100 missions, which is what the shuttle was sold in 1972 to Congress, that we were going to use each orbiter about 100 times. And that's interesting that the engineering certifications did want to look that far down the line, because the most experienced orbiter in 30 years was, of course, Discovery with 39 missions. You were looking that 100 missions. That's interesting. So that would make it robust, I think, and on there. The other thing to think about, people, particularly if you're under 40 years old, no Gorilla Glue, no underwater tape, none of that stuff you see on TV. You guys pioneered that type of super strength materials probably with trying to do what you were doing.
I think there were, a lot of manufacturers that were sought after to develop materials for all kinds of components, and including TPS. So
I like the story about how you waterproofed all this. Tell us the off-the-shelf product you used to waterproof the
So, I mean, the factory waterproofing was a vapor phase silane deposition done in a vacuum oven. But after you fly the vehicle, it is an organic material, and it decomposes at about a little over 1,000 degrees Fahrenheit. And so the vehicles have to be re-waterproofed, or had to be re-waterproofed between flights. And so they would use we started with another silane product originally, but we had some trouble with that, so we reverted to Scotchgard, which is a household name, a 3M product originally, and used that for the re-waterproofing, which was for those of us that had to apply it, not such a great experience, but it certainly worked, and didn't work great, but
did you use it right out of the
work.
can, or did you have a
We had large cans,
Okay.
and it was pretty full on. I mean, there's a lot of tiles to waterproof. So.
Absolutely. Well, and who'd have thunk it? Who'd have known that in there? Well, we're enjoying a conversation with Jeff Andress here. There is your dad on the right. Tell us about that picture.
So I think he's up on the Ohms pod working with Nick and John Bjornstead, and they were probably just going over some paperwork for some work they were doing on the Ohms pod. I say that because Dad didn't work the vertical stabilizer. He worked the Ohms pods, and he was an inspector there.
That'd be the vertical stabilizer right there to the left of the picture.
That's
probably.
correct. Yeah, the leading edge of 102.
Well, what a nice picture of your dad there, and the good old days there. And we got a few pictures that Jeff showed me here that we put on Facebook to advertise your appearance here on Stay Curious. I just love looking at these people, that every one of them is a national treasure. They did a job that it's hard to reproduce in society today.
Yeah, that's right.
Unless you're going to be working on the Dream Chaser or SpaceX or something like that, right?
That was the KSC kind of full. That was everybody that was hands-on thermal protection near the end of shuttle program. And so the integration folks from the orbiter processing facilities, inspection, engineering, the guys from the thermal protection system facility that was manufacturing and processing those goods to get ready for integration. That's the whole group there. So
good memories there. Who
cool
you
picture.
see there in the middle, Marty, in the beige shirt?
Yeah, it's Terry. Terry White. Yeah.
Terry White's in there. Got to call into Terry. He'll be on our program next week. He talks about, he's the shuttle garage manager in there, and Gene Wright's in there somewhere, and maybe Brian Lohas, a few of the TPS people I've had the privilege to meet. There's a young Jeff Andress there. Got your grandson Jason here and your wife Donna. What do you think of Grandpa there, Jace?
Cool.
Okay. Yeah, if you want. Yeah, Marty, go ahead and swing that around. Yeah, why not? Swing that around and wave Donna, your wife's here. Yeah, just go ahead and swing. Yeah, there you are in our Stay Curious studio there. Say hello.
Hello.
There you go. Glad to have you there. Jace is in 6th grade, and he likes recess. So, anyway, it's fun to look back at when we were young. And what's that particular? Was this your help with STS-1? Because that's the coin there.
Yeah, that's what the left side is, just the letter and the medallion they handed out to everybody that worked STS-1, and then the picture on the right. There's an insert picture there with me doing some work on the payload bay door, I think of 103. Might have been, I can't remember if it was 99 or 103. I think it was 103.
Mm-hmm.
There had been an incident where a bridge bucket let go inside of the OPF, and it damaged the payload bay door. And so they had to repair the graphite epoxy on the payload bay door with a doubler, and then we had to install blankets at a very quick manner, and so we used kind of a new process to do that. And so it was a team award that I participated with that team rebonding the blankets on the payload bay door.
Well, that's a cool memento to have for sure. And this is what NASA did a lot to the contractors did to their workers. That is a coin with contains material that was flown in space on Columbia. And we see those in our auctions and eBay and stuff all the time. And, I won't take less than $40-50 for it. So anything space flown's worth 20. You got the paperwork and all, but this, and then you had another little bit of, I'm glad you included these things, not only local newspapers, but the trade magazines and so forth, always promoting the technicians and the people behind the scenes, like these two that you sent us here.
Yep. And the one on the left there was some folks at the Thermal Protection System facility, Martin Wilson and Dennis Stanifer in the picture with me. And we had developed a process on site at Kennedy to manufacture the insulation blocks that the tiles are machined from. And that had been some technology that was transferred from Lockheed Missiles and Space out in California to us, and we had some NASA specs, but other than that, it was up to us to develop a process where we could basically provide the ability to produce this material for the life of the program and stop relying on an external source.
Okay. Here's another little certificate just to show people what was that accommodation?
So that was the same process, bringing that processing line up to speed for shuttle.
We're going to talk about that processing line here in a minute, how unique it is. Why choose this as a career? And talking to Jeff earlier, I told him I'm going to point out that go into engineering, kids. Jace, go into engineering. Do not go into liberal arts if you want to make money. All right, like I did. This is a future career. I mean, we're always going to need this, right? It's always be evolving. So, shuttle success, working in operational spacecraft.
Yeah, I mean, if you're interested in space flight, I mean, if you were going to bring a vehicle back from orbit, you have to have insulation. You have to have something that will withstand the heat loads, and and so. Yeah, I mean, it is one aspect of spaceflight. It's not quite as cool as rocket engines, but if you're into materials, it's definitely.
You could argue even more important, getting them back. Believing in reusability of thermal protection as a key component. I want to contribute to a better solution.
Yep, that's right. I think that one of the things that I learned through shuttle was that evolving is like super critical. It's really something that's hard to do but is necessary if we're going to actually do some of the things that are our goals now to become interplanetary, or to have like rapid reusability even for low Earth orbit. We need to upgrade. We have to have better materials that perform not only better, but are more manufacturable and cheaper, right? I mean, it's incredible how much money we spend on the space shuttle, and so to be effective, we have to find lower cost means to do this effectively. I mean, think about, the story that I hear repeatedly is if you threw away an airplane every time you flew in it, how much would it cost you to get a ticket from here to San Francisco? I mean. And essentially, this is why rocket reusability is so important. And I think this is engaging work for decades forward. Because Earth atmosphere is one atmosphere, but Mars is another, and so the heat loads are very different, and the insulations and the ways that you passivate that heat load have to be very different. And so as we discover new environments and want to go to them, we have to develop new materials and ways to be successful.
Great point. And also the trajectories coming back to Earth might need more fortified tiles and so forth if it comes in faster.
That's
As we
right.
talk about.
The heat loads change.
Those change in there. We're going to talk more about these tiles a little bit. The projects that you've been involved with. Look at this, folks. What Jeff has been involved with. So just highlight a few there for us. X-38 in the middle there. That's our mini shuttle, top secret space plane. Two of them at least are housed over there in the old OPFs. Dream Chaser. That's going to become a player here in the next few months, we hope.
I certainly hope so.
The Orion back shell tile development collaboration. Tell us about the Orion spacecraft and what you've been involved with.
So yeah, I mean, those guys were originally Orion was going to have an ablative back shell rather than tile, and as the vehicle got heavier, they started to have to increase the thickness of that ablative material, and it was basically a cork micro balloons held together with silicone product, SLA 561, and the thicker that material got, it started to exceed its structural ability. So it wasn't going to be able to withstand the loads coming back in, because of how thick it would have to be to protect thermally. And so they started looking for lighter weight options, and tile was a good candidate for that. And so this is how the TPSF made the shift from shuttle tile production into tile production for the next NASA program, and so fortunately I was able to be a part of that, and they started to use one of the more thermally capable products that we used on shuttle, an AATB, an alumina enhanced thermal barrier material with an impact resistant coating on it. And so this is what the black tiles are that you see on the outer back shell of the capsule now, and so far it's been very successful, and I'm pretty happy to have been able to work on that. We allied with Lockheed Martin, who was the prime on the capsule, and all the installation work was overseen by them, and they did the design on the tiles, but we definitely collaborated on the material development and did all the production of those tiles for Lockheed.
Now, you being at the early shuttle program, of course, there was, my question is there a university or institution that is teaching tile technology? My point being, you all pioneered it from the beginning by trial and error, okay? No one went to a school and learned how to do tiles, all right, correct?
That's true. I mean,
so today, is there a university that's saying, come to us, we'll teach you thermal protection system technology? Because that's what I find interesting about the shuttle era is so much stuff you had to invent on not necessarily on the fly, but yes, as you were progressing and building the orbiters and the infrastructure, the reality changed things. There was no school to learn how to do some of this stuff. I mean, the basic physics, of course, and I'm not talking about that. I'm talking about making these silicon tiles out of sand and air. And you guys pioneered that here at the Space Center.
Yeah, I mean, I think the answer to your question is no. That is not out there that I'm aware of.
Okay.
So
Jace can't go to a school and learn TPS technology.
He cannot.
That's sad, kind of in a way.
He could go to a school and learn about material science.
Okay.
We could go to a school and learn about chemical engineering.
Yeah.
And those would be helpful, certainly. But as far as the actual how-tos and why, it's there. There's kind of a vacuum there. There's a void, and the community's not huge. I mean, I know people at NASA Ames Research Center, and at Johnson Space Center, and the TPS community nationwide is not a huge community.
Mm-hmm.
It's relatively small, and
okay.
And it's very difficult to attract and hold young people in this industry. We're finding, and I think that. It's not as exciting as some of the other roles in spaceflight, and so And also it is very much aligned with a production facility. So it's not just the engineering of it, it's the actual making of it. And there's a lot of getting your hands dirty in there. And I think also the answers aren't easy. And so it's a tough sell. We went looking for candidates over the last couple of years to bring in to kind of learn this business. And it's difficult to attract people and it's difficult to hold people.
Well, that's an interesting angle on it there. But also, to me, people that want to be in it seems like they have an opportunity to excel. So if they would get it on there. Marty, you've got a question on our UCX family microphone there.
Yeah, Jeff, who actually developed the tile? Was it Rockwell, or did they subcontract that out?
Actually, it was a fellow that was working for Lockheed, a guy named Robert Beasley. And he was a Stetson graduate. And he went to work for Corning in New York, Corning Glass Company. And he started messing around with these glass fibers. And he had some interest in them as an insulating material. And Corning really didn't have any interest in developing anything like that. And so he found some interest at the Lockheed Missiles and Space Company in Sunnyvale. And he moved there. And they actually then were getting interest in the shuttle contract and looking for a way to implement that, an insulating material that could be used on that vehicle. And so they started to create a process for manufacturing these products. And so he's the guy. He is the father of tiles, if you will, in my mind. And
Name again?
Robert Beasley.
Robert Beasley.
There's a book out there called the Shirt Sleeve Invention that is about his life story. It's not riveting, but it does kind of give a little background to how things got going.
The Shirt Sleeve Invention by Robert Beasley, father of the silica tiles. That's interesting. Good question, Marty. Well, let's look at a couple other things. Tile production unit manufacturing process. This is the code words for their materials, or?
Yeah, so Shuttle started out with all silica products, which were a 9 pound per cubic foot or a 22 pound per cubic foot material. And so that made up all of the insulation on the shuttle and the original design. But we were looking for stronger materials early on, and so NASA Ames Research Center came up with another product which they called Fricky 12, which was the 12 pound material, and it was a composite. It actually used some other fibers, a ceramic fiber, and in so doing made a much stronger material when it was cast and sintered or fired. And so we used those stronger materials on like the leading edge of the elevons, around the main landing gear doors, nose gear doors, where you had more structural loads on the vehicle. Originally, those were the heavier 22 pound per cubic foot material, and it was really good for high heat loads, but not as strong as the 12 pound material that was the composite. And so in 1981, they certified the Fricky 12 composite material, and so it went into use in a lot of the areas that originally were 22 pound material. And so then in about 1998, a fellow, Dan Leiser from Ames Research Center, presented some papers at the American Ceramic Society that were talking some test work that he had done with alumina enhanced material, and he was taking a 20% alumina fiber and some other ceramic fibers with the silica fiber, and he was coming up with a material that had a little higher temperature capability. And the real goal there was to be able to apply a coating that was more impact resistant. And so the way he did that was with a dispersant coating, something that soaked in and created more of a crust on the tile rather than the thin glaze coating that had been on the tiles previously. And so in doing that, he found there was quite a bit of deformation when you fired that coating onto these insulating materials if it didn't have that higher capability that was created by the alumina fiber. So this was the introduction then to Shuttle for the alumina enhanced, the ATB materials. And so that has been kind of like the forward work, is to optimize these composites. They're still mostly silica fibers, but there's other ceramic fibers that are in use today that do give a little better thermal capacity. You can get higher heat loads, and in so doing, work to make better, more impact resistant, higher thermally capable coatings. So this is the future.
Evolution thing in there. What these different type of heat shields? I want to mention that thermal protection systems were thought about in the 1950s for reentry of nuclear warheads.
Yep.
Right? That's sort of where all this started.
Yep, that's
And the
right.
Corona spy satellites too,
Mhm.
their reentry film containers.
Yep.
Are you, is
I
that
don't-
something you like?
I don't know
research?
much about the Corona film cameras, but or film cases.
How about
but
ASSET? ASSET
I've read
is
a
a
little,
program
I've read a little bit about
was-
asset.
they've got it out at the Sands Space Museum, and ASSET, it was ASSET was an acronym for testing the first of these. But this goes
Yeah.
back to the 50s.
Yes, that's right.
and still refining this technique here. How are these things made? Here's your basic recipe up there.
That's scary. So, I mean, all of these, all of the tiles are basically a fibrous ceramic, very low density, because they need to be able to be stable at high temperature but not weigh anything. So you want something that is like capable of 3,000 degrees Fahrenheit but weighs like balsa wood. And there's not a lot of materials out there that are capable of providing that. And so that's why these products are somewhat niche. They're specialty in that they're really good for a pulse heat protection insulator, not so much for steady state. And we just the materials are the fibers are very small. They're in the 1 to 5 micron range, so really tiny, no mass. So when you cast this stuff up, you slurry it in water, you chop it up, and then you put it into a mold. You pull all the water out and you compress it, and it makes this nice kind of brick. And then it goes into a kiln and you fire it at really high temperature, and it fuses all these fibers together that make it this nice rigid ceramic that you could machine. And the magic of that is that it's a 90 to 93% void, so it's mostly air. And so when you heat load it, you expose it to a really high temperature. It takes a long time to translate that heat across all those fibers. So the back face still stays nice and cool, and it takes a long time to get it hot enough where it's a problem for something that would oxidize or would melt at a high temperature. So, like I said, very, very niche kind of product,
Yes.
very one purpose.
I hope everybody's enjoying this conversation with Jeff Andrus. I'm learning so much about the tile protection system. You're doing a great job of explaining it very simply there, Jeff. Our collections manager, Nick Enix, who you met, we were going to get a tile out of the case, and it's one of the cases it's kind of hard to get our tile out of. But if you haven't held a tile in your hand before, a bag of marshmallows is about 3 times heavier than that. But what amazes me is if this was the tile in my hand, Jeff could have not a Bunsen burner, but a blowtorch on one end of it, and I wouldn't feel the heat on the other
Yeah,
end.
that's right.
And what is? But this is a TPS family outing. All right, Marty, that Nick gave me to kind of show thermal protection system facility. Susie Cunningham and Jean Wright remember this building real well. This is a family deal out there. You probably had your wife Donna out there with that, maybe. But what it says here on this, by the way, I want to know who this guy is with that great mullet.
That is Dan Whitaker.
All right, Dan, there's Dan Whitaker right there. There you are, Dan. Beautiful mullet there, man. There's a sew arm thing that looks like that was used to put the blankets around the engines. But it says here, it is the thermal protection system, a 2-story, 44,000 square foot building. It is the only facility in the world that can manufacture a tile from raw materials to be ready for installation on a spaceship. And there's about 17, I counted, manufacturing, repair, and processing areas. 17 of them. The vacuum chuck and pressure pad manufacturing shop is one of them.
Yep.
So is that true today? I mean, that's unique. And like I said, the university was there at the United Space Alliance coordinated facility there on Kennedy Space Center, and no universities take it upon themselves to try to teach this. That's kind of, I kind of find that odd, but maybe somebody will. But tell us about that, how unique it was and one of a kind.
Yeah, so I think there were a couple of guys, trying to remember the NASA guys' names that were really the proponents of developing the thermal protection system facility. Bob Ketterer was one of them.
Mm-hmm.
Drew Evans, I think, was the other gentleman. And those guys, they really had a vision for, it was very difficult logistics scenario for the shuttle program to have all of the manufacturing of the thermal protection components done on the West Coast in California, and then have to transport those commodities to Florida for installation on a vehicle. So, if you had any mishaps along the way where you had tiles that didn't fit when they got here, then you had to remake. Just the time lag and the scheduling associated with that was really burdensome to the program. And so these guys started thinking about a way to have that capacity on site at Kennedy Space Center. And so that's what the thermal protection system facility was really all about. And so we stood up a machine shop, a coating shop. At the time, we weren't manufacturing the insulation material or the coatings. We were still buying them from Lockheed Missiles and Space Company, and this was like 1988, I think, is when we brought the TPSF online. And we stood up a soft goods manufacturing area. That's where Jean worked, and Janet Mills, and just a ton of ladies that were very talented.
So sisters.
That's right. And they manufactured just hundreds of different configurations of gap fillers, thermal barriers, all of the seals for every gear door, every vent door, every place that they were designed in. And the blankets for the upper surface were all manufactured in there. We brought a lot of tooling. We remanufactured tooling for making these custom parts for everywhere on the vehicle. And so this was it started in '88, but it was still evolving all the way into the 2000s for sure.
It says 90,000 different parts made in this facility.
Yep.
And Jean Wright's a great friend of our museum, been on our show before. She's got a children's book that she's authored out there about the So Sisters.
Nice.
That'll be out in November. So, Marty, a comment.
Yeah, Mark, I just looked this up, and this little note is probably a few years old. As the Space Shuttle program nears retirement, NASA is looking for ways to preserve the program's history and inspire the next generation of space explorers, scientists, and engineers. NASA is offering 7,000 shuttle heat shield tiles to schools and universities that want to share technology and a piece of space history with their students. So it looks like some universities may be teaching.
Good.
They're
Thank you for
making
looking that up, Marty. And boss Karan Conklin's in here. You're needed at our board of directors meeting briefly, Marty.
Yeah.
So I can handle the show here from there. But all right, let's look through here. Let me go up there. Boundary layer transition flight. Let's pass by that. Look at this. Or you want to talk about that? You got some points you want to make on that?
Just that was a really interesting project to work on. We did an experiment. NASA did an experiment where they flew a protuberance tile on the left wing of both 103 and 105 shuttles, and the purpose was to try to intentionally trip the boundary layer which is the plasma flow or the layer
Mhm.
between the plasma flow and the tiles early, so that boundary layer transition could be measured.
We're going to see pictures of that in
So,
orbit
yeah.
here in a minute. And we've learned that from Terry White, the orbital processing manager, when on 114, I think it was Steve Smith, no, Robinson went out there and pulled the gap filler out between there. It's amazing how one little thing, just a quarter of an inch up over this giant spaceship, can affect the whole dynamics, correct?
It's pretty amazing.
So
But
this was an experiment to look into that.
that's right.
And in one of those dark tiles there, beneath the Elveron.
Yeah, that's right. This let's see if I can point to it right in that area.
Okay.
Is where the protuberance was,
All right.
and then there were thermocouples on the surface of tiles downstream of that.
All right.
That were measuring the temperatures as the vehicle re-entered.
All right. Marty, comment?
You got a question from Robert Law. Was
Robert
challenge-
Law's in Dundee, Scotland,
Okay.
watching today. Great to see you, Robert.
was
Sorry.
chal-
Yeah.
was Challenger the first shuttle to have thermal blankets?
Was Challenger the first shuttle to have thermal blankets?
Yes, I believe it was.
You go out and see beautiful Atlantis, which I did this weekend. I saw it again, got tears in my eyes. I went to the whole spiel instead of going in the back door. I get teared up watching that. That's one of the greatest reveals of anything I've ever seen. And one of the first things I remember seeing is it's covered in quilts.
Yeah,
know,
that's right.
And then we learn about Jean and the Sew sisters, and that was a transition from the tile all over the place we use in these reentry blankets in the cooler areas. Tell us a little about that.
So, I mean, the blankets were a great transition because the tiles initially, they were the white coating was not as robust as the black coating. It was different composition, and the maintenance associated with those white tiles was huge. And a lot of the white tiles were also diced because of the structural loads, the locations on the vehicle where they were bonded, and so. The blankets were much more conformant and also could accept those higher flexure loads that in those areas of the vehicle. And so also you could cover, a 30-inch by 30-inch section of the vehicle at one time rather than, multiples of tiles. And so the weight went down, and so did the maintenance significantly with the addition of the blankets and the removal of those white tiles in most of the locations. So it was a great mod for the vehicles.
If you remember on STS-1, they had some tiles off of the orbital maneuvering pods, the cheeks and the rear end there that's got the engines in it for maneuvering in orbit, and those tiles were missing, and then years later those became blankets over the OM pods there. Yeah, I could see where it'd be a lot less maintenance, just making sure those things were tucked in just right in there. Here's this experiment that you purposely disrupted the plasma flow by putting these little things on a tile.
Yep.
So how did that work out? What was the
I think that the real takeaway from this was that it helped NASA to refine some of the thermal models associated with boundary layer transition, and so there's a lot of conservatism built into those models intentionally, but it allowed some refinement to occur that gets those models in a more realistic condition and helps predict heat loads better. And so I think in that respect it was a great success. We went in really conservatively, and it took the program kind of a long time to be open to making the protuberance larger and larger to get a greater effect. But we did end up flying I think a half-inch high protuberance, which doesn't seem like a lot, but it did give us some good data. Another byproduct of that, there was some catalytic coatings that we flew that were proposed by some folks at Ames Research Center, Mark Resinen, for looking at what would potentially happen on the Orion spacecraft back shell, because the flow tends to reattach after it comes off of the heat shield on the upper surface of the back shell. And so there was some thought that the catalyticity associated with that reattachment might lend to some higher heat loads. So they tried to artificially introduce those properties on shuttle flights, but we didn't get hot enough to do that. So,
Well, it has been pointed out, 12 years since the last shuttle was wheels down. It was always an experimental vehicle, people are saying now. And there, again, you're always fine-tuning something in there. And yet a great vehicle. Jeff, right above your head is a tile there that I didn't get to bring one in. It's got a bunch of numbers on it. People that see these tiles in captivity, like our museum, or maybe you've gotten to buy one at one of our auctions. Tell us a little bit about those numbers that are on there.
So one would be the part number, and the control number that would be traceable back to its manufacturing documentation. So we would know the serial number and of the insulation billet that tile was machined out of by that number. The coating and the coating lot number would be associated with that control number. All of the machining data. So it would be traceable all the way basically back to, the theory was that it would be traceable all the way back to the raw fiber and glass powder that were used to make that part.
Well, I've got a question. Why didn't you use a barcode? I wonder.
We tried.
Okay.
But the fidelity of the barcode after flight was a problem for rereads. We also tried messing around with QR codes for a while.
Well, that was kind of pioneering back in the day.
It really was, and it was
QR
was
codes were
longer
so
ago
big
than
now.
you'd think.
I didn't know QR codes in the 90s.
They weren't calling them QR codes when we were messing with it, but there was a company that I think Vera Label or Vera something.
Okay.
Anyway, but again, the oxidation associated with reentries kind of tough to get things to survive, and so even if you pretty much eroded most of the paint away, there would still be kind of an outline there that you could usually still read. And
okay, well, good. That's a great explanation for that. One of those. Here's a group of people underneath an orbiter there. Recognize a few of them there, and Miklos is there. You've got the Sokol photographer up there in the middle there. You've got listed here. This is the BLT.
Yep, that's right.
Group as an acronym. BLT sounds good to me.
Yeah, sounds good to me too. But
right.
that was not what the acronym stood for.
What does it stand for?
It was actually the boundary layer transition flight experiment. Yeah. So that was the protuberance tile, and those were a lot of the folks that worked on that.
One of the tiles is up above your head.
That's right.
I got you. And you're not going to notice it's one of the dark ones, I think, right?
Yeah, that's right.
And a quarter of an inch or half an inch up there. And who are some of your friends there?
So Jimmy
you see any of these
Carter's
people
there.
very frequently? Or?
I see Jimmy a couple times a year. Brad Wilson is still working at the thermal protection facility. So is Jimmy.
We saw Ann this weekend. Miklos there in the dark sweater. Saw her at the Sands History Memorabilia Show. She had a booth there. And so did Sokol there. He had his photography. So you see the smiling faces, the dark hair, and what's that mean to you to see this crew of people?
There's a camaraderie there for sure. We worked together to a common goal, and it was on a big program. And a lot of those people. I remember Ann when she hired in as a young engineer, and was working on instrumentation on OV-103 for the Western Test Range, and she kind of took over that role, and that was I've known Jimmy since 1979 when I hired in as a tile tech. Known Brad. Brad's mother actually worked in the thermal protection system facility up in the textile fab area, and Theo Spanos was a young engineer that came on board with Shuttle later in the program, but was really enthusiastic. Really dug his hands into it, and was just really thirsty to learn a lot. And good people. Good memories, good people.
That's excellent. I'm jealous because places I worked, like the newsrooms I worked in, we never got together for any pictures or anything like that. Though a bunch of us photographers running around there, we got pictures of people looking stupid, but not an organized group shot there. So always great to see the smiling faces. That was the boundary layer transition team there. And some more happy pictures that you gave me here. Endeavor's obviously out on the pad there.
Yep.
Again, a chilly day. Must have been 50 degrees out that day, huh?
Yeah, it was a little cool.
On there. Any special occasion that you remember this photo op was done for?
Yeah, I think it was probably, it might have been it wasn't the last flight.
133?
It was late in the program. It was one of the last
134
opportunities.
was Endeavor. Yeah, 134 would have been Endeavor.
Yeah, that's the Thermal Protection System Facility Group.
Mhm.
That's everybody.
And again, another picture of them from an orbiter. Looks like Atlantis in the background.
Mhm.
And so always nice to have that. And awards day and
Yep.
nice picture of the VAB.
Yeah, that's I think everybody there I know. Martin Wilson, he's one of the guys that really
Who's
had-
Martin Wilson?
Martin's the guy in the center.
Okay.
And I still work with Martin. He and I, we got into kind of a collaborative working relationship at the Thermal Protection System facility, and he had a very strong material science background. He was a material science engineering major, and then also had a pretty deep background in ceramics engineering. And he really kind of both whetted my appetite for materials and just kind of helped keep my curiosity about why this stuff works alive. And I knew how to kind of get things done in the shop, and Martin knew the materials, and so we were kind of a really good team for development. And so a lot of the process development at the TPSF was a collaborative effort between the two of us and other people at the TPSF as well. And we're still doing that.
We're going to talk about the future here and what you're doing. Something popped into my head. Would any of this thermal protection system technology be useful in building homes? We're seeing this horrible fire in Hawaii, and we've seen them in California and everywhere in there. Has there been any thought to the housing industry incorporating some of these to at least resist fire? I don't know if it would work, but just that's a spaghetti on the wall thought there, Jeff.
Yeah, I mean,
See if
the
it
short
sticks or
answer
not.
is a little bit.
Mhm.
The longer answer is that the fireproofing is very different than insulating from reentry heating.
Right.
And so most of these materials are expensive, and they have to be highly purified to survive with the high temperatures in an oxidizing environment. And so yeah, it would work.
Not a good side
but,
hustle then.
Yeah.
At the moment here. Okay,
That's
all
right.
right. That's another one down the drain there. Marty, we got a comment there, buddy.
Yeah, Mark, do you really think you want woodpeckers pecking on your house? And
There
do you
you-
want to Scotch guard your house every few weeks?
There you go. Exactly.
Yeah, that would be bad.
We're winding down here with a great conversation. What are you doing today? What's your dream chaser footprint there?
So I did a little work with those folks. They were taking pretty much a tiled approach to their thermal protection, but a part of their solution involved a newer material that NASA had developed, tough rock, and I really can't go into too many details about that other than it's more of a carbon-based system.
Tough Rock. What an acronym that is there. Dream Chaser is the mini shuttle that Sierra Nevada has been they've flown it a couple times, actually. I think not to the space station, a drop test maybe, but it's never been in orbit.
Drop
has it?
test. They have not been orbital yet.
First, it was going to be crewed, but now that's down the line. But it want to make a cargo ship to the ISS.
That's right. They're contracted for that.
And what are we looking at here?
Just some tough rock samples that we
Okay.
did for our jet specimens. Just one of the testings that you can do here on Earth without flying back from orbit to kind of represent the environments as an arc jet test, which is a plasma generator plasma tunnel, if you will, where you generate a plasma flow over the surface and can kind of represent what's happening in a reentry, going from a very low pressure, low oxygen or no oxygen environment to one that's fully oxidizing. And it's a way to test on land. It's an expensive way to test typically, but it is a viable test for.
How big is that? Is that my coffee mug size?
About that, yeah.
Okay, all right. Looks like that stuff you put in your truck liner.
Kind of does, yeah.
Yeah, all right. The Orion, your footprint on America's new moon ship. So
Yeah, we talked a little bit about that already. I mean, we did produce all the tiles for those folks, still being produced today at TPSF for future Orion spacecraft, and really happy those guys are still doing that work at the Thermal Protection System facility.
Okay. And the borosilicate glass frit and coatings development.
Yeah, this is some work that we did for United Space Alliance. When shuttle was coming to an end, the Lockheed folks were concerned about having enough materials left over from shuttle to keep making tiles for the Orion, which was a legitimate concern. I mean, there was quite a bit of that material left over, but how much you were going to use based on their schedules at that time was going to be more than what the residual was. And so we started looking at how to produce some of these materials, and one of those was the borosilicate glass frit, which is used as one of the main component for most of the tile coatings. And so this was a very niche product that was done by Corning, glass company in New York, and it was very expensive. Involved some commercially available at the time Vicor glass, which is a porous glass. Borosilicate glass, and that company stopped producing that glass because Vicor was used basically for things, glassware that needed to be highly shock resistant, thermally shock resistant. So headlamps, labware, that kind of stuff, and all of that's gone to sol gel type processing today. It's not these high energy, super energy consuming process where you have this melt glass, and the energy associated with these processes and cost is really high.
Technology's
as the market
changing.
falls off, right. So Corning sold the plant that was producing the Vicor glass, shut down the line that was making the frit for shuttle, and as a byproduct of that, we needed to figure out how to do that for the future of Orion, and we did. So,
So when your source dries up, you find another one, and
and
Corning.
Sorry, that's a story that has kind of been a theme throughout shuttle. I mean, that was the purpose of the whole NASA shuttle logistics depot being developed down in Cape Canaveral. Was that you had these like hundreds, probably thousands of contractors that were out there, little shops that produce these one-off items for all kinds of components on the shuttle. And as they either grew and decided, hey, this isn't worth the amount of time and energy that it takes me to put in to produce this product that has all these requirements for shuttle, I don't want to do it anymore. Those manufacturing processes had to be brought in-house, and so NASA contracted with at the time Rockwell and then Boeing, USA, and to keep these processes and manufacturing capabilities alive to keep sustaining the shuttle, and so it became a very logistics driven part of the business. And
That's interesting. These niche little areas that were suppliers and then didn't find it affordable or just didn't want to live within the government specs.
yeah, all
and
kinds of black
you guys had-
boxes and electronic components and antennas and comm stuff, hydraulics, valves, you name it.
seals, all
windows,
kinds
yeah.
of stuff. Amazing. Things you don't think about. Hope you've enjoyed having Jeff Andress tutor us a little bit about thermal protection systems. I certainly learned a lot, and Jeff, you've done an excellent job explaining something complicated. There's a little more to develop that we were talking about there. Marty's handed me some of the people watching the show today, and you might know a little bit about the TPS on the next slide that comes into existence. There you got the large-scale production, and you're talking about the large-scale production that's going to be needed for this, a unique picture of the SpaceX Starship out there in Texas. So love the solar halo around the sun there, blocking it out there. But Jeff, I know you can't tell us a whole lot about this. Jeremy Andrus is watching.
Oh, cool.
Okay.
Great.
Cliff Watson is watching in Sonoma, Australia.
Wow.
Hey there, how's your brekkie today? And is it getting finally cooling off down there, Cliff? We got Per Carlton. Tonight's Falcon 9 Starlink's launch is pushed back to 9:55, y'all. So thank you, Carlton Bailey, 5 minutes before 10 for that launch. Another noisy rocket blasting off the Space Coast here.
That's right.
Interrupting our sleep. And Neilio 30's watching. We said hi to Robert Laub in Dundee, Scotland. Bill Whiting's up there in Michigan. Mark Usiak and his brother Tom are getting ready to come down from Lancaster, Pennsylvania, and they'll be on Stay Curious Saturday or Friday. Dave Stangy's watching up in Michigan. Space Monkey is a follower now with us, and Doug Forrest is a artist in California, Los Angeles, and he is practicing drawing shuttle tiles on his beautiful pencil renditions of the shuttle there. So really appreciate you being here, Jeff. What can you tell us about this behemoth of a spaceship?
It has some of the similar requirements to shuttle in that it's a large body. It has to re-enter Earth's atmosphere. It's going to get hot.
Other than that, you have to watch, I guess, Ellie in Space, who's been on our show. She does a YouTube, and some people camping and living out there. And we love it, and it's progress, and obviously SpaceX has proven that their method of just keep building it and destroying them until they work he's had over 200 first stages come back.
That's right.
And the first 18 or 19 failed, correct?
Yep.
And so you're enjoying working for them?
Yeah, absolutely. I mean, it's a very progressive environment, and some really talented, very intelligent people I get to work with.
Well, it seems like they've snagged a pretty intelligent person to help them out there. I'm happy about that. Some with your expertise makes me feel better. Doesn't you, Marty, that this shuttle expert's working on the next great space plane? So.
It's been a great opportunity. I mean, to kind of be able to go to hopefully the next generation vehicle. Certainly was appealing, and it's been difficult and challenging, but also pretty rewarding. And,
Good.
So
you do a lot of it. Are you allowed to live here with your family, or you go to
yeah.
Texas a lot? Or
no, actually, the tile manufacturing is happening here in Florida.
Okay,
that was attractive.
all right.
So.
They're building a new facility at KSC. Is
Yes,
that going to
that's
be
right.
where it's at?
I think
eventually?
that eventually there's a possibility of that. Yeah. And
Okay.
It's had a lot of consideration. So.
Well, Jeff, I've really enjoyed our conversation.
Yeah,
I
thanks,
hope
Mark.
you all have enjoyed it out there. Is there something I didn't ask you that you'd like to share about this tremendous shuttle era that you were part of, and your rich future with SpaceX?
No, I'd just like to reiterate how fortunate I feel to have had the career that I have. I would like to encourage anybody that's young that has any aspirations to do something like this, to definitely engage at every opportunity you could get, because I started off as a high school graduate, bonding tiles as a technician, and here I am 44 years later as a development thermal engineer for SpaceX. And, I really think that if you apply yourself and you have interest in it and it stimulates you, that it can be a career. It can be at least rewarding, and you might be able to make a living out of it. Maybe you can make a good living out of it. So,
Yeah. Up
and
to you.
the world needs you, so do it.
Great. The world needs you, and they bring on the heat, the tile people there. We didn't say that enough this program, but thank you very much, Jeff. Really mean that sincerely. Marty, we learned so much, and you really were easy to understand. Tomorrow we've got astronaut Mike Baker on a recorded program. So because that's recorded, we won't be celebrating 3 astronaut birthdays. We'll be celebrating that on Facebook. Kathy Thornton, who's out at the Space Center right now, is the astronaut of the day. Her birthday's tomorrow. Tom Henney, he had a space flight or two. And Canadian astronaut Thirsk, forget his first name, but they were all born on August 17th. As well as my daughter Jessie. If you're watching, happy birthday to you. But so hope that y'all check out our program tomorrow. And Friday we've got Carlton Bailey, who's telling us that the launch has been pushed back to 9:55. We got some tremendous storms going on right now. And Tom and Mark Usiak, all 3 of them rocket hobos, are going to be on Friday. So Marty, thank you for a great Streamlabs production today. Anything we need to button up over there?
Nope, we're good to go, Mark.
All right. Appreciate that. Again, thank you, Jeff, for a wonderful program. Glad to have your wife, Donna, and grandson, Jace, here. And so until tomorrow, I'm Mark Marquette saying we can't wait to see you with astronaut Bakes, Mike Baker, all to bridge the space between us. Good job. Thank you a lot.
Thank you, Mark.